Water and ocean structure, ocean chemistry, topic 1. Water, familiar, abundant, and odd. Familiar, abundant, and odd. Standing on the shore and looking out to sea, the boy said, "There's a lot of water out there." And the wise old oceanographer responded, "And that's only the top of it." This is a quote by Richard Ellis from Singing Whales and Flying Squid, but there's a lot of truth to this quote. Here's a puzzler for you. What is HIJKLMNO? Do you have any idea? Take a guess. I have to warn you, it's a lame joke. It is the alphabet from H to O. That's exactly what we're going to be talking about today. We're talking about water, and the chemical formula of water is H2O. So this was just a lame joke. So the water molecule is held together by chemical bonds, and I'm going to be talking about these chemical bonds in the next slide. But here on the bigger image, you can see what a water molecule looks like stylized. The two blue balls are representing the two hydrogen atoms, and the chemical breakdown you can see in the smaller diagram. It has one proton and one electron. And the protons have a positive charge, the electrons a negative charge. The bigger red ball represents the oxygen atoms. And oxygen has the chemical symbol of a big O. And in the lower right, you can see what the oxygen atom looks like broken down. In the nucleus, it has 8 protons and 8 neutrons, and then it has 8 electrons. Going back to the figure on the left, the sticks between the oxygen and the two hydrogen atoms are. So here in this diagram, you can see what the water molecule forms. So you have these two hydrogen atoms that have an electron and a proton. They share the electrons with one oxygen atom, which is a bigger atom in the second panel. And together they form a water molecule. And the bond, because they're sharing their electrons, these kind of bonds are called covalent bonds. I don't want to get too much into chemistry at this point, but if you have any questions, feel free to contact me. So this water molecule that results is shown in the image to the right. Properties of a water molecule. So the water molecule is composed of 2 hydrogen atoms and 1 oxygen atom, and they are bound together by this covalent bond. This is a kind of chemical bond where they share electrons. The oxygen atom is bigger than the hydrogen atom and pulls the shared electrons, which have a negative charge, a little bit closer to the oxygen. Because the electrons have a negative charge, the side of the oxygen of the water molecule has a little bit of a negative charge, and the hydrogens will have a little bit of a positive charge. So overall, this molecule does not have any charge, just that one side is a little bit more negative, the other is a little bit more positive. And that's an important property that plays into why water is so special. When I see these stylized water molecules, it always reminds me a little bit of a teddy bear or of Mickey Mouse. So here again is another view of that shared electron picture of the water molecule. So the O pulls the electrons a little bit closer, and so the oxygen side becomes a little bit negative, and the hydrogen side becomes a little bit positive. And therefore, because it has a positive and negative side, water is also called a polar molecule. So in this slide, I would like to point out something else. So again, you see the polar water molecule of water. And what I want to point out is that the bond angle between the two H's is 105 degrees in liquid water. Just keep that in the back of your mind. We're going to come back to this again later. Now I would like to talk about another kind of chemical bond, and these are hydrogen bonds. These hydrogen bonds are much weaker than the covalent bonds that hold together the water molecule. The hydrogen bonds link water molecules together by electrostatic forces. So the polar molecules attract each other, and they form this lattice of hydrogen bonds. So the positive side of the water molecule, the H's, they line up with the negative side of the water molecule, the oxygen. And so you can see in this picture, the hydrogen side of the water molecule is always attracted to the oxygen side, or the oxygen side of the water molecule is attracted to the to the hydrogen side. So because of this, we have cohesion. That means the water molecules stick together, creating surface tension. And adhesion is that water molecules stick to other substances. I always find this term hydrogen bonds misleading. And so you have a little cartoon that pops up in my mind when I think about it. It is not that the two hydrogen atoms are attracted to each other, but it's always the oxygen atom of one molecule and the hydrogen atom in the other molecule. The cohesion property of water gives water its surface tension, and that's why, like, some insects can walk on water. Water is very unusual. Water's temperature affects the density of water, and water is the only substance on Earth that naturally occurs in its three natural states. And a state is the expression of the internal form of a substance. So water on Earth exists as gas, such as water vapor, liquid, as in water, and a solid, such as ice. So let's look at the upper panel. So gas is a substance that can expand to fill any empty containers. Atoms, or the molecules of gas, are in high-speed motion and move in random directions. You can see this if you have this beaker and you push the big piston down, you can compress the gas. Then in the middle panel, it shows you the liquid. So a liquid is a substance that flows freely in response to unbalanced forces, but has a free upper surface in the container it does not fill. So the atoms or molecules of liquid move freely past one another as individuals or small groups. When you push the piston down, liquids can compress only slightly under pressure. And solids is a substance that resists changes of shape and volume. A solid can typically withstand stresses without yielding permanently. A solid typically breaks suddenly. So just think about an ice cube. When you take a hammer, you can just smash and shatter the ice. So on Earth, water can occur in all of these three states: gas, liquid, and solid. So and here's the property that makes water unique. Water becomes less dense when it freezes. So just think if you had a vat of liquid iron and you had a big iron block. If you dump that iron block in the liquid iron, that lump, that solid block, would sink to the bottom of the vat. So water is the only substance that behaves differently. If you have a cup with water and you throw in an ice cube, that ice cube will float. That's very unusual. So in this picture, you can see the lattice structure of an ice crystal. And you can see this hexagonal arrangement at the molecular level. So I told you before to remember the bond angle. The bond angle in liquid water is about 105 degrees. So what's the angle between these two hydrogen bonds? And in the solid, in ice, that bond angle increases to 109 degrees. So this is the angle between, if you think about the mouse ears or the teddy bear's ears. So in that space that you see here, the same space could be occupied by 27 water molecules in its liquid state, but only by 24 water molecules in its solid state. So water expands about 9% as the ice crystal forms. And because of the way the water molecules are arranged during freezing, ice is less dense than liquid water and it floats. We can see water in its gas phase. So water vapor is invisible, but as it evaporates from the sea surface and rises into the cool air, it can condense into tiny droplets that form clouds and fog. So in this picture, you see a low-lying fog bank, often seen around the Golden Gate Bridge in the San Francisco Bay, when warm, moist air passes over cold waters of the California Current. The air is cooled to a saturation point, and some of its water vapor condenses into fog droplets. Water's temperature affects its density. So in this diagram, you see the relationship of density and temperature for pure water. So on the x-axis, you have a temperature scale in centigrade. And on the y-axis, you see the density grams per cubic centimeters. One is more dense than 0.09. So the higher up you go on the scale, the denser the material gets. If you go towards the origin, the lower the density gets. And you can see the two parallel bars on the y-axis that just indicates that there's a chunk taken out of the axis, so the axis fits on the scale. And the temperature again on the y-axis, you can see 0 degrees centigrades with this 32 degrees Fahrenheit, the freezing point of water. So let's start at the right end of the diagram at point A. It shows the density of water at 20 degrees Celsius. As we are cooling the water and moving towards the left, the density slowly increases as heat is removed. And at around 4 degrees centigrades, 3.98 centigrades at point B, water has reached its maximum density of 1 gram per cubic centimeter. And then as we continue to cool the water, something odd happens, that the density decreases again. And as we reach point C, that's 0 degrees centigrades or 32 degrees Fahrenheit, the freezing points, the water is at its least dense. And we get this abrupt decrease in density with freezing. And again, you can see the note, the break in the density scale as we have reached the density of ice. So here in this diagram, you can just see that ice floats, it is less dense, and warm water is less dense than cold water. So the spaces in the water the spaces between the molecules are bigger in warm water than in the cold water. So in cold water, the water molecules are more tightly pushed together. Water in many ways is an unusual molecule and has some unusual thermal characteristics. Water has high heat capacity, which means it resists changing temperature when heat is added or removed. And you can think about it, if you're walking on a hot day barefoot on asphalt, the asphalt or the sand on the beach can be really, really hot that you can burn the bottom of your feet. But then you step into water and it's nice and cool. Even though it receives the same sunlight, gets the same energy, the sand or the asphalt heats up quickly because it has low heat capacity, and the water resists the changes in temperature, and we call this high heat capacity. So your book has this table with heat capacity of some common substances. So again, heat capacity is the measure of heat required to raise the temperature of a substance. And water is said to have a high thermal inertia, and that is the tendency of a substance to resist change in temperature with the gain or loss of heat energy. And in this table you can see some heat capacities of common substances. By convention, pure water has heat capacity of 1, and you can see any of the substances above have much lower heat capacity. Granite, which is our continental rock, has a heat capacity of 0.2, and the only substance on Earth that has a higher heat capacity than pure water is ammonia, liquid ammonia. Before we finish with this topic, let's do some quick concept check questions. So here's the first question. What are bonds that are formed by sharing of paired electrons? And I'm going to give you a little bit of time. They are called covalent bonds. Here's another question. The Planck of water allows individual water molecules to stick together. The correct answer is hydrogen bonding. Hydrogen bonds greatly influence the properties of water by allowing individual water molecules to stick to each other. What property of water is responsible for the amount of time it takes for water to boil? The correct answer is B, heat capacity. Because of the great strength and large number of hydrogen bonds between water molecules, more heat energy must be added to speed up molecular movement and raise water's temperature than would be necessary in a substance held together by weaker bonds. Liquid water's heat capacity is therefore among the highest of all known substances. This means that water can absorb or release large amounts of heat while changing relatively little in temperature. Another question. What is the only substance to have higher heat capacity than liquid water? And the correct answer is ammonia. Of all common substances, only liquid ammonia has higher heat capacity than liquid water.